Hi everyone, I am Marie from the French Competence Center, part of the EuroCC project. And with Karim Azoum and Pierre Aubert from the LAPP in Annecy, we organize the Grey Scott Thursdays and the Grey Scott School. So welcome to this new Grey Scott Thursdays webinar. Today's session is a little different from our usual technical deep dives, but it remains closely connected to the technologies and trends shaping modern HPC, of course. Before we begin, a quick update on the Grey Scott School. The countdown is officially on. The school starts in just 3 weeks, and we're incredibly excited to see the community growing. So we have now reached more than 650 registered participants and 18 satellite sites across France and Europe, making this the largest edition of the school so far. So a huge thank you to all of you for your enthusiasm and support. And the good news is that it's still possible to register, of course, whatever you want to attend the full program or just selected days, it's still time to be part of the adventure.
Could a simple chemical reaction teach you how to unlock peak performance on today's supercomputers? Welcome to the Grey Scott School 2026, a free advanced summer school on high-performance computing, designed for professionals from industry, public sector organizations, and academia. From June 22nd to July 3rd, 2026, join us in Annecy, France at LAPP, at one of our satellite sites across Europe, or online via live streaming. All courses are taught in English. You can pick the courses most relevant to you or dive into the full 2-week program. You'll learn the practical behavior of modern hardware and how to write performance-optimized portable code. Week 1 focuses on CPUs, Week 2 on GPUs, covering architecture, bottlenecks, parallelism, memory, and performance analysis. All learning is built around a single challenge: simulating the Grey Scott reaction. Simple to start, yet complex enough to stress compilers and expose performance limits. You'll explore modern tools, languages, and libraries such as C++ 17 and 20, CUDA, Fortran, Python, OpenMP, TBB, Kakos, PyTorch, and more. The school provides ready-to-use container environments for smooth hands-on sessions. Expert instructors from CNRS and CEA guide you with live Q&A and community support on Discord. Satellite sites let you learn together locally without traveling. Want to host one? It's easy with our turnkey setup, sharing the school with your colleagues and ecosystem. You'll leave not only with hands-on HPC skills, but also an official certificate of participation. And you know what? You can start early with 18 Grey Scott Thursdays webinars, weekly from January 29th to June 11th, introducing summer school concepts and new topics. Whether you're an industry professional, engineer, researcher, or student, if you have programming experience and want to push your skills further, this program is for you. Register now at cc-fr.eu and start learning today. Grey Scott School 2026, Europe's leading HPC summer school.
So if you've been hesitating, now is the moment to act. We'll share all the registration links in the chat. And today's webinar will be presented by Pierre Aubert himself, who will share his feedback and key takeaways from the GTC 2026. So Pierre will help us understand the major announcements, emerging trends, and what they could mean for the future of HPC and scientific computing. Pierre, the floor is yours.
Yeah, thank you, Marie, for the nice introduction. So yeah, today I started a long time ago, in fact, for the feedback on the GTC, but this one will speak about the GTC 2026. So GTC stands for GPU Technical Conference, so it's the conference of the year of NVIDIA mainly, but not only. So to get all the news from the hardware, the software, everything we can have to do some HPC, some machine learning, everything. So of course, it's a really dense conference. There are a lot of parallel sessions. So I will not summarize 900 talks. Of course, it's not possible. So I invite you to see the presentation catalog if you want. You can click here, or you can have the link on the keynote on YouTube if you want. Today, we will mainly focus on the new hardware evolution, because we have some new hardware to play with, and evolution also of the libraries of the tool and the whole ecosystem from NVIDIA mainly. Some feedbacks from people who do crazy stuff with simulation, with analysis in general. And we will finish with a small bonus. It's kind of the usage now for the GTC. So we will finish with something which is not totally related to HPC, but a little bit. You will see at the end of the presentation. So let's start with the hardware. And of course, it was teased last year. Now we have the Vera CPU. So the next generation CPU from NVIDIA. We start with Grace in 2023. And now we have Vera. So Vera is a CPU based on ARM also, so 88 Neoverse cores. So the point was to have enough cores and enough threads to be sure that once you are using agents, for example, the GPU is not limited by the CPU, because if the GPU starts an agent and the agent is using a tool, the tool runs on the CPU, but if the CPU is slow, the CPU will slow down a lot the GPU. So they add more core for this purpose here. So we have 176 threads with SV2, so the elastic vector register, if you want. So 6 times 113 bits. So it's a 6 times SSE4 if you want, in terms of vectorization. So you can vectorize 24 floats at the same time. We have 240 GB of memory, so LPDDR5X, so the same for Grace, but a bit boosted, of course. And there is a special multi-threading now, so it's a bit different than before. So here you can have 6 vector registers to vectorize, but you can say, okay, now I want twice the number of threads, and each thread will vectorize only 3 times SSE4, so 3 times 118 bits, and not 6, but you can have 2 threads running at the same time, vectorizing several different part of data if you want to do some computation, some independent computation. So you can have a boost like this, so it's called special multi-threading for this. We have some caches, so L1 64 kilobyte here, so quite standard right now. 2 megabyte of L2 and 162 megabyte of L3. So you can do some stuff with a big cache like this. Olympus can decode 10 instructions per cycle, so it's a bit more than Grace, but only 6 for Grace. So you have extra. We can have extra instruction decoding at the same time. That's why also there is a big cache for instruction. Normally it's not 64, not 64K, but in that case they boost it a bit also. There is a memory system resource partitioning and monitoring, so to monitor what's going on this CPU, so the MPAM. There is a new the NVLink C2C second generation for 1.8 terabyte per second of bandwidth. So if you want to transfer data from Vera to another GPU just for the next slide, or to Vera if you want. And they recommend, if you want to use a Vera, to have GCC 15.2 or LLVM 22 or later. And you can use the -M CPU Olympus to specifically target this architecture if you want. So that's for the CPU. Now we have also a new GPU. The Rubin GPU was teased also last year. And here we have 336 billion transistors and 2.5 trillion more for the memory. So it's a really, really huge hardware. So 288 gigabytes of memory, so way more than before. 22 terabytes per second of bandwidth, so huge bandwidth also compared to before also. For the inference, we have 50 petaflops for Float 4 and 35 for training in Float 4. So again, Float 4 is not what you are thinking. I explained that in the GPU webinar. So it's not only a float with 4 bits. Of course, it's ridiculous. So it's much more than this, but I don't have time today to explain that. So go see the other webinar if you have questions. In terms of Float 16 and Brain Float 16, it's 4 petaflops. And for TensorFloat 32, it's 2 petaflops. So there is a typo in the datasheet, unfortunately. So they call 2 teraflop and not 2 petaflop, but I'm pretty sure it's 2 petaflop. Otherwise, it's not coherent with the other parts. So first time I see a typo in the datasheet of NVIDIA. And then if you want to compute in Float 32, 130 teraflops, and Float 64, 33 teraflops. And don't be afraid, as I mentioned also in the previous presentations, you can use some tricks. You can use tensor cores if you want. You can emulate this precision and get 400 teraflops for floating point 32 SGM, so single precision general matrix multiply, if you emulate the precision, and 200 teraflops for float 64, so double precision general matrix multiply, again emulated. So it's really, really powerful. So I did a full part of my presentation on GPU to explain that. It's really powerful. So don't be afraid. There is less hardware to perform this kind of computation, but you can still emulate and get really good performances. And there is a new NVLink, also 3.6 terabytes per second of bandwidth, if you want to connect also Rubin together. So there is a new one, also Grok. So it's a LPU. So LPU stands for Language Processing Unit. So basically you want to boost LLMs to make sure that they are really efficient in terms of computing. And Grok 3 has not too much memory, 500 megabytes of memory, but really fast memory. 152 terabytes per second of bandwidth, so huge bandwidth compared to the previous one, of course. 1.2 petaflops of float 8. So again, it's not really, really float 8, but you get the idea. And 98 billion of transistors. So it's way smaller than Rubin, but still you can do some stuff with it. So you can pack all these Grok 3 chips into a big rack and get 138 gigabytes of memory, 40 petabytes per second of bandwidth, 315 petaflop of computing with float 8. And of course, you can stack the whole chips, so you can scale up to 256 chips in the same rack and get 640 terabytes per second scale bandwidth. So if you get all the chips together, if you really want to have really efficient inference or efficient training, you can do this kind of stuff if you want. So that's for the hardware. So in terms of roadmap, we are just here. So everything is on time, of course. So we will get Rubin Ultra next year, or the new generation next year. We will talk to this about that next year, of course. There is an extra news related to the hardware. They pass all the tests to be in space. So you can have a Vera Rubin device in space. They pass all the tests that we do, of course, for the space engine, because of course you are exposed to the cosmic rays. You have a lot of problems to deal with. So they pass all the tests, even for this architecture. So remember, it's a 4 nanometer architecture. And they managed to pass all the tests. So big announcement also. So it's still 1 kilowatt. So you have to get the power for that. But in terms of computing, it's okay. So nice point here. So that's not, of course, totally the end of the hardware, but let's move about the software now. So NVSHMEM got some updates. So to remind you, NVSHMEM is a tool which is capable to do a lot of communication. So you can make point-to-point communication from one GPU of a rack to another GPU of another rack, of another blade server, as you want, or two GPU close together, of course, no problem. That's the same API for that. And they manage a lot of communication protocols. So they manage NVLink, InfiniBand, Ethernet, a lot of stuff, of course. So it's based on OpenSHMEM. It was one of my questions for the Cocos webinar 2 weeks ago. So this is the reason. And it's a scalable point-to-point communication software. So it's important, of course, if you want to scale. Yes, really what matters most here if we do some computing. There is a symmetric allocation pattern, so to avoid a lot of checks which are unnecessary if you guarantee that there is a symmetric allocation. And you can, once you communicate, you can have a GPU initiated operation. So the kernel can talk to another kernel of another GPU. So the GPU talk to another GPU. But you can also initiate operation with the CPU. It's possible. And you can use the classical CUDA, the CUDA streams, the CUDA graphs. Everything is supported. No problem with that. And it's the fabric of Magnum IO. If every time you want to do some data exchange or communication, Magnum IO is based off NVSHMEM for that. So in terms of communication, we have a first feedback here from GROMACS. So GROMACS is a simulation for molecular dynamics, so simulate molecules. So you can find new drugs, you can find new chemicals, stuff like this. And they had first implementation with MPI, of course, because everyone starts with MPI. And the point is, once you compute on the GPU, because of course it's really heavy computation, so you want to use the GPU first. Once you finish an iteration, you have to synchronize to the CPU. Then you want to do the communication with the CPU. Then you resynchronize with the GPU, and you resume the new information that you get, and you start a new iteration. And of course, that's a pity, because from this time to this time, you have no computation at all. That's another problem that was addressed by NVAPISH2. I talk about that in 2024. The very big problem with the communication like this is you do your computing, you stop everyone, you do the communication. While you are doing the communication, nobody is computing at all. So basically your computing center is waiting, and then you resume your computing. And that's a really big problem of the whole-to-all communication if they are managed in a naive way. And the problem here is it's 10 microseconds for the whole operation. And of course, it's a bit too much for at least for what they want to achieve in terms of performances. So they did the implementation with NVSHMEM with all the tricks that comes with NVSHMEM. And the point is you can do your computing, you can initiate GPU communication, everything is asynchronous, and then you can compute again with an overlap. And that's it. That's okay for that. You break the synchronization, you make everything asynchronous, and it's really efficient. So it's only 1 microsecond. There is a huge gain here in terms of latency, in fact. And they guarantee that you get the maximum compute communication overlap. So NVSHMEM will do its best to make sure that it's efficient. If it's not possible, it's not possible, but you will get the best scenario possible each time. So we stay on the GPU, which is really important because, of course, the GPU, you don't want the GPU to wait. So stay on the GPU and do maximum stuff on the GPU. There is no CPU-GPU synchronization, so everything is asynchronous if you want to do some stuff. It's really important also. And we have some news with NVSHMEM, Nickel, and Nixel. So NVSHMEM, as I said, you get GPU-initiated communication and symmetric memory. Nickel, I presented that before, but I prefer to be brief on that. So it's another communication library for GPU-initiated networking. So you can have classical point-to-point communication, ring communication, and since last year, they use symmetric memory allocation, such as NVMe, because of course they had a big problem of latency and of checks, because of course, if you don't have symmetric memory allocation, every time you jump on a node, you have to check if you get all the information that you want. And if it's symmetric, you don't have to check because by design it's symmetric. So it's if you manage to get the allocation, it's okay. There is now an inspector. So if you want to debug Nickel workflow, you can. It was a bit difficult before. And there is also a real-time congestion feedback. So every time you have some congestion in your networking, so you have basically a route, or you are fighting on some routes to exchange data, you get a feedback and say, okay, don't communicate from this point to this point with this link because it's busy. So use another route. We'll get all the information for that. And the last one is a new one, in fact, Nixel. So the idea is to have a new communication ecosystem, but for low latency data transfer, because it's really important for what will come next in the presentation. And they managed to get from 480 microseconds to 50 microseconds on the DeepSeek. So if you use a neural network and you have a lot of communication, you have a lot, it's a big model, of course, you have to communicate between GPUs, you have to manage some memory, we'll see that just after. It improved a lot the performances, so it's important also to have that in mind. They developed Nixel only for this purpose, and you can also manage some memory, so data movement on memory, on the disk, on the SSD, on the S3 storage, if you want to have more persistent storage. So you can have all this stuff, and we have a roadmap for the first half of 2026. So it's almost okay now, almost done. In March, it was not the case, of course. Now there is a DSL support for NVMe, so to have a high-level language to manage communication. They can register user buffer, so they managed to improve that, so quite nice. For the InfiniBand non-blocking, the RMA, so the remote memory access, it's also ongoing, and they also now support a TMA, so the thread memory accelerator. So remember, I presented that also for a few weeks ago on the GPU webinar. TMA is a new part of the chip since Aubert. The idea is to make sure that once you have a thread and the thread wants to access data on the memory, the chips here, the TMA computes the address for the thread. The thread does not have to compute the address itself. It was the case before. Now it's not the case anymore. Of course, you have to deal with that because it's a new part of the chip. And now it's done it's on the roadmap for NVMe. Normally it should be quite okay right now. For Nickel, we have elastic buffering, port recovery, and also a TMA support because it's really important to have that for the new architectures. So now it's also ongoing. And the last one for Nixel, we have the DLCL support also because it's important. There is a load balance and failover, and they will support also the S3 RDMA, so remote direct memory access support. So once you have a different memory and from a device hardware, you can see the memory of the other hardware as it was quite the same. You get this implementation in Nixel. Of course, it's really important for low latency data transfer. And there was an optimization also for, I think it was for Nickel or for MVAPish maybe. No, for MVAPish last year, I think, on GTC 2035. If you want to have a look, you can do some crazy stuff with RDMA and RMA. So if you want to have a look, you will get all the information here. So I have to speak a bit about transformers because a lot of news are orbiting about how to optimize transformers. So really quickly, I will have to take a moment to explain that. So once you have an input, so you want to put the input into a layer, and once you have a sequence, so tokens, for example, you pass your sequence into the layers, and you get a response from this layer to this sequence. And you do that for several other layers. And this is called attention. So the attention is all you need. The famous paper about that. That's this paper. And then you pass the same input into these new layers to get another point of view, if you want. And then what we do is we take the first layer, the first answer, we do a matrix product with the second one. We get combination matrix. Then we perform a softmax of this matrix. And we finally multiply this combined answer, if you want, this trick combined answer to the final matrix that we get. Of course, they are not trained the same, exactly the same way. And then we finally get the output, and we get the sequence of output for this. And it's okay. So once we speak about attention, that's the principle of attention. And that's why also transformer takes a whole part of the game here, because it's really powerful in terms of coherency of the output. But there is a problem, of course, with that. And that's why we are talking about key value, KV cache, stuff like this, and everything has to be clear. So we get something like this. We will forget about the softmax for this slide. It's not important. We have an input, but of course the problem is I have an attention layer, so I need two matrix products for a new token. That's a pity, because of course, if I do that, I have a lot of redundant computation, and of course, computation costs a lot, and I don't want to recompute my matrix product every time I have a new token, otherwise it costs too much. So the trick is to say, okay, I know already that if I have this sequence and all this sequence, everything is okay, so I can cache everyone. And if I cache everyone, I can say, okay, let's append a new token here. If I do that, I have a new token on the blue and on the green matrix. I know for sure if I compute this matrix products, I will get this on this result, so I don't have to do it again. And I can say, okay, let's just compute the new part. So here I compute this matrix product to this vector to this vector to get this one, and this matrix product to this vector to get this one. Only that. So I save a lot of time by doing this. Once it's done, I perform my softmax only on the, which is new, in fact, of course, because otherwise it's okay. And then we append the new token here in the last, the last matrix, and we also compute only what's new. And with that, we can have a new output, and we update only this output. So we save a lot of computing bandwidth with that, but of course, we need extra memory. So we need a bit more of memory, but we need more, we save a lot of computing by doing that. The more we have new tokens, the more the context is long, if you want, the more you gain, of course, because at the end, you get only the last row. It's a matrix vector product and not a matrix product. So of course, it's not the same complexity, and it's okay to do this kind of stuff. Of course, it's quite difficult to manage everything because you have to manage data. Before it was only input and output, and now you have to manage data in the middle, and of course, they are quite huge. So there is Dynamo now for that. So the idea of Dynamo, and a lot of softwares now are orbiting around Dynamo. So I need to be clear on that. It's a framework, an open source framework, to make sure that you can have a large scale inference services. So if you have a computing center and you have a lot of customers and they want to do some requests, so basically LLM request, so with PyTorch, with TensorRT, with GL, VLLM, whatever you want. You want to be compatible, of course, with everyone, because you don't want to force your user to use this or that software. But you want to manage everyone in a nice way. So first, you want to manage the KV cache, all the KV stuff, so key value stuff. So we have a block manager and a router, of course, if to start the computing, you want to get the cache where you need it, and not another place. Of course, you want to cache also maybe on NVMe information if you don't need them again because you have a bit of latency, because the user is doing something else, but you know that the user will come again to show that it's not too much delayed. And of course, the low latency is managed by Nixel because it was designed for that. So Nixel is the manager, of course, to deal with all the low latency data transfer, so to be sure that everything is efficient. And there is a GPU task scheduler for that also, because of course you can split a lot of your computing because you have big models. Models have a lot of tensors, and you can split the computing of each tensor on several GPUs. You manage the KV cache for each GPU to be sure that everything is efficient, and you use the GPU at their maximum speed. That's the goal of that. So there is a disaggregate serving for that. So you get the request of your user with a big request, and you split it into a lot of pieces because of course you can split the model, you can split the tensor, you can split everything to be used really efficiently. And then we have also a topology optimized serving, so it's Groove, and of course Groove is based on Kubernetes, and it's basically Kubernetes with topology information. So you have the topology information of your whole computing center, and then you can optimize all your data transfer, all your communications, and it's really important. If I want to quote myself, you can see normally the GTC of 2023 with NV tags, and NV tags was designed to optimize that. So it's NV tags, boosted NV tags with Kubernetes. So everything is upgraded compared to before, of course. So by doing that, they achieve 7x speed up on DeepSeek mainly when they did this kind of stuff. So it's a lot, in fact. Once you optimize everything under the hood, it's really a lot. So it does matter a lot to do that. So here we come to GPU partitioning because, of course, we have two different ways here. We have the first way, which is, okay, I want to use my full GPU for one thing because I have a lot of users and I want to be sure that everything is efficient. But of course, you can think the other way and think, okay, I have huge GPUs now, Rubin, Blackwell, and how can I use the full GPU at its maximum speed because I have to compute so much things at the same time? Maybe my simulation is not that performant. How can I share my computing resources? So that's a big problem, and you have a lot of solutions for that. So first, you can use CUDA streams. So you have several streams, you stay on the same process, and you say, okay, everyone can get a part of the computing resources, and if I manage it well, it's supposed to be okay. But as Stephen Jones reminds us at the GTC, of course, it's an opportunistic parallelism. So if it's possible, if it fits, it's okay. But if you have one stream taking too much resources, the other will have to wait because they cannot execute their kernel at the scale they are supposed to. So that's a big problem, and that's a really tricky point once you are doing stream. It's not free. You cannot say, okay, I have a stream, it's consumed not too much, I can use several streams and it's okay. No, you have to say, okay, my stream is using half of the GPU. I can have another stream using the half of the GPU, but if my stream use a bit more, you are stuck. You will have to wait, and you will kill your performances. So that's a bit annoying. On the opposite, you can say, okay, let's pretend that my GPU is several GPUs. So the multi-instance GPU, so the MIG, which we have the MIG since Ampere, so it's 2020. So there is a fixed GPU partitioning. So you call basically NVIDIA SMI, and you talk to the GPU, and you say, okay, let's pretend you are divided in 4, up to 7 for Ampere, for example, M100. So you have isolated instance, and of course here you see immediately the problem. Blue can have 2 instances, okay. Orange can have 1 instance, no problem. But green cannot have 1.5, and you will have a fight here for the resources at some point. And if you are using, for example, HT Condor, you cannot have this fight because, of course, orange reserve this instance, so green cannot access this instance because we are talking about several processes. So they cannot fight, or if they fight, maybe you did something wrong in your job, or you have several processes in your job and you have a problem. Not really flexible. Okay, we can do another trick. We can say, okay, let's use multi-process service, so the MPS. So you can say, in advance, I have some processes and I want half of my GPU from process A, another part for process B, the rest for process C. Okay, no problem. But if it's a fixed part of resources, so if at some point of your computing you say, okay, B wanted a bit more, you're stuck. If you want C to have a bit less, you're stuck. If you want A to have a bit less and B to take over, you are stuck. Okay, we have a problem. So let's make some room because the problem is modern workloads are unpredictable. So you need flexibility, but you need efficiency also. So, okay, let's make some room and let's think with another stuff. So they introduce this year the green context. And the idea is to have a lot of context and to say, okay, I make my partitioning well, and I say, okay, A will have this part, B will have this one, and C will have this one, and everything is nice. And we will have controllable partitioning. You can do that on the fly, so you can dynamically reconfigure because maybe A use less memory, less resources, but B needs a bit more for this particular part. So you can adjust on the fly this part, so you don't have to struggle with the stream or to have fixed resources for the other. And the point is it's a single process. So the big problem of the MPS here is you don't share information. So if you are using, for example, the same description of the GPU, because of course it's the same GPU, or you are using the same base information or the same read-only data for whatever reason, you are stuck because you will have several copies of the same data for each process and you lose a lot of space on your GPU, even if we have a lot of space on the GPU, but still at some point, if you want to use the GPU at this maximum capacity, it's a pity. So here we can share all the data between contexts. It's really important. And here you ask the process, okay, I want this and this context, and everything is okay. Of course, we can do other tricks, but we'll see that a bit later. And it's more flexible. And by doing that, we can also have an upgrade of Insight to see what's going on with the context. So here you have all the green context here, and you have the detail here. So you can see, okay, what I'm doing, which data I am using, the result, stuff like this. So you have all the information in a high level part. So that's a nice update of Insight. And you can see the resources and the physical placement too. So you can see, okay, my green context is here on this GPU, and maybe I will move it or whatever for whatever reason, or scale it, or shrink it, whatever. You have the information on what's going on during the time, so it's really, really powerful. And of course, you can use a lot of patterns with green context. It's not static. So I presented you the dynamic partitioning. So you have the partitioning, you can change it on the fly, but of course you have several. You can have a low latency reservation. So you can say, okay, I want to be sure that this part of my GPU is reserved for really low latency processes. So if you really have a real-time analysis or something like that, you can say, okay, I want this to be really fast. The rest I can use classic computing and classic synchronization, but I want this one to be really fast, and you can have that. You can have overlapped execution. So maybe you have a context doing some computing and another doing some data movement, and they can overlap a bit, of course, not too much, but a bit. So it can save you, of course, not to be stuck. So it's possible. And the last one is you can nest context together. So you can have a main context, and in it you can have several. So for example, you can have a really fast context for the low latency, and then have, okay, maybe I have another context from this particular purpose and another one for this other purpose. You are free to do what you want for this, and it's really powerful. So there is Qtiles also on that. So I presented it a bit briefly last year, but here we have some news. So of course I have to talk about that. So Qtile is a new idea. So once you want to compute some data, sometimes you don't want to be bothered with the word detail of the architecture. Of course, you have to know it at some point, as Alice mentioned in our presentation. But of course, at some point, you don't want to have this level of detail. Maybe you just want to say, okay, I want to split my data in several blocks. One block is roughly a streaming multiprocessor, because I have to be aware of my software and my hardware at some point. But that's it. I don't want to deal with much detail than this. And you can split it this way. You can change the way it's split, and you have corrective operation on these tiles. So you can stack, you can exchange data, you can do some computing, you can call some kernels on them, and you can change the way they are split, because maybe for this particular kernel you want to another split, or for this particular simulation or whatever you want to do. So you can split in more fashion. And we have some news also this year. So there is a support the scale, so you can scale from one CPU, one GPU to a full computing center. So that's the idea basically of the Qtile. So you say, okay, I want a high level split of my data, and then I let the software does magic, and it's okay. So here we have some news. So it works with CUDA graphs. So if you want to mix that with CUDA graph, it's okay. And it's working with Python, with C++. It's an official support. And for Rust and Julia, there is a project from the community, and you can use them right now if you want, if you are curious. So big news from Rust if you want to have a look also, compared to what I said just last week. And to get into the details, so I will stole the idea of Bryce, who presented that, of course, at the GTC. So you have the classic stack here, so you can call a high-level program, then you have the cuDNN stuff, or you have the BLAS stuff, and then you have cut class, and then you can do some CUDA call, kernel, stuff like this. And then we have the representation, so LLVM, for example, if you are familiar with, of course, and the PTX, and then you can run on the GPU if you do that. And for the Qtile programming model, they change it a bit and say, okay, let's use the Qtile at the same level of the kernel, for example, in terms of complexity. And under the hood, what we will do is a brand new intermediate representation and a brand new compiler for that. So you have a dedicated compiler to compile your Qtile program, so it's not anymore the same as before. So for tile optimization, for now, so brand new compiler. Of course, we don't have enough compiler in the HPC SDK, so let's have one more. Not a problem. We have something like 35, 36. I lost the count. One more. Why not? After all. So here's an example of course, from Bryce, from CUDA. So it could change a bit with the time, but here you can have an idea of what's going on. So I define a kernel here, a kernel with Qtile, so the kernel will accept tiles, and I can perform a small computation here with my tiles. I can partition my tiles so to get some views, and then I can get a swizzle here to make some computing and get my load. I create some matrix multiply for this. So you can, basically a tile is a matrix, so you can do whatever you want with it, and then you can store it. So that's quite simple to do. The good news is you can use it right now because it's CUDA 13.1. So I do have some 13.1 on my laptop, so you can use it too, no problem. If you have an upgraded driver, it's okay. You can do the same in C++, not totally yet because we have to wait CUDA 13.3, but it's quite the same. You define your kernel, but it's a __tile ___, not an ___ global or device as we can have before. Here's the tile. So new keyword to compile it. And you can do basically exactly the same API. So you can change the same partition, the tile, the swizzle, you can do some matrix multiplication, you can do everything that we did before. They want to have an upgrade also. I forget to put that in the slide, of course, too much information, but they want to have an upgrade. For now, you cannot mix the tiles and the kernel as you want. Sometimes you have some limitation. For the future, they want to be sure that everything is smooth. And if you want to create a kernel like this, but you say, okay, I want to support kernel, I want to support tiles, I want to support everything, it will be possible at some point to do that. Not now, unfortunately, but it will be possible at some point. So flexibility will come, and it's really, really nice. Of course, you can do the same in Rust, in CUDA 13.1. So right now, if you want to play with Rust, you can have. So I have the link also. Can give you the link if you want to play with it. You have to get Rust. You have to get NVIDIA CUDA Oxide, which is a Rust implementation of CUDA, the wrapper of CUDA. So you can play with that if you want. No problem. And here you can see it's the same. So we have a proc macro here. So if you don't know what is a proc macro, you can have a look to the webinar of last week, of course. We explained that much better than right now because I don't have so much time for that. So you do some magic here if you want, and you define your kernel to run with tiles, and does the magic for you, and you can do the same as before. Of course, it's the same API. It's really coherent, so it's really nice to have this kind of stuff. So what's next for the future? Okay, so we have to do a lot of stuff. So speaking about Dynamo, because as I said before, a lot of programs are orbiting around Dynamo. So they want to update Dynamo. So for now, we have the high-level software, so PyTorch, TensorRT, stuff like this. So you can have several instances, of course, because it's not really well split. Then we have framework, kernel generator, custom kernel that you can develop for your application. They will use certainly CUDA X library. So CUDA X, so you have 250 library, a bit more. So the QBLA, the QFFT, the QRound, etc. All these kind of libraries. Then they will use communication libraries, so Nickel, Nixel, NVSHMEM, stuff like this. And then you have the CUDA driver, and you talk to the driver, and you talk to the GPU. And everything is really nicely done. And of course, that's only the surface of the problem, because I love this slide from Stephen Jones. The reality is everyone is trying to hack everyone else to gain some call and to be faster. And that's a mess. That's a really big mess. And you have no control. Everyone is calling everyone else. There is hack everywhere. So we need something more to be sure that everything is scalable and everything is nicely done. So let's get rid of everything, and we really need a more efficient way to use multiple GPU. So, okay, what do we do? So what will come, it's not there yet, of course, it's in development, but I'm pretty sure that if they announce that, it's quite okay normally. What they want to do to scale everything nicely is to say, okay, we have one layer for everyone here, for all the high-level libraries, all the level frameworks. We have one layer for all the frameworks, the kernel generator, the custom kernel. Then you talk to all the CUDA X libraries at once, whatever, which node, which GPU, we don't care. Then you have communication library to handle also the magic for the communication for the CUDA X libraries. And we have something which is missing, which is really important. Because of course, at this point, if I develop a software which is aware of the topology of my favorite data center, I will have a problem because if my neighbors use another software or develop its own software with another hierarchy or another naming convention, I will say, okay, this is, for example, this is a node 1, and I want to talk to the node 1 and to get on the node 42, whatever. Maybe another program will say, oh, this is a node 33, and we have a problem. And you cannot put this information into these libraries because they don't know, in fact, and they are not coherent. So we need an extra way to make sure that once I call the node 33, I'm sure this is a node 33 for me, for PyTorch, for TensorRT, for all the CUDA-X library, for everyone. Otherwise, we have a problem. And for that, they want to build a new driver, a multi-node CUDA driver, which can run all the CUDA driver from all the GPUs at the same time. And the driver, this driver will tell, okay, you are talking to the node 33, you are talking to the node 1, you are talking to the node 42. And it's not your choice. You ask the driver, okay, where am I? And tell me where am I? And by doing that, they have a full unification of the communication, which is really important. And they will do that. So be prepared to have a new driver on top of the other to manage the full blade server, the full rack for you with a coherent way. So this will be really important for the future. And for the news, we have some news also coming from Nsight. So not yet, of course, in the future, but we'll have a lighter Nsight container. So remind, last year I told you that Nsight is cheap inside containers also. So you can spawn an Nsight container in your favorite cluster, Kubernetes cluster, for example. It's possible. They will have a multi-node profiling, so you can profile thousands of nodes if you want. So for really big computing center, it's really important. So we'll get this kind of heat map to have a really high level view of what's going on. It's important. So they are working on that. It's not finished yet, but it's on the road. And they will enable qtile profiling. It's not there yet, of course. It's a bit young, but it will come at some point also. So that's for the future. And they will be also able to call Nsight directly from Python. So use a decorator here, and you can say, okay, let's profile this particular function, and you will get only the performance here with this function. Really powerful, really, really powerful. And so you can still normally call, of course, you can call NVTX, you can call this kind of stuff. I speak about that last year. So you will get NVTX for Python, for C++, for Rust, no problem. But here you have an extra way to profile. If you want to have only one kernel, for example, maybe you don't want to start the whole Nsight, possible. And for qtile, we have some news also in the future. So they will support Ampere and Ada, so the L40, 4090. Ampere will also have a support from qtile. It's not there yet. And there will be a support for C++, as I said before, but for Hopper also for qtile. Of course, everything runs on Blackwell for now and on Rubin. That's the purpose of qtile, but you will have an extra support for the older GPU also. And for now, there is a big limitation on qtile, unfortunately. For now, qtile manage only power of 2 tile size, and of course, they will break this limitation in another release, of course, because that's a pity, of course. Life, unfortunately, is not made of power of 2. That's a problem. I'm a developer. I know it's a problem, but yeah, that's kind of a big limitation. So be prepared also if you run qtile. If you don't have power of 2 tile size, you will have a problem. So do your best to avoid that, at least for now, until we get the nice update. So let's talk about some climate simulation evolution. So people are doing crazy stuff with climate simulation. So of course I have to talk about that. So the state of the art for the best multiphysics simulation is around 200 kilometer resolution. So this kind of resolution for the global Earth, of course. So this is done by Econ, the Econ simulation. So they did some atmosphere the ocean and the land simulation. So you have all the three, and that's really difficult to do, in fact. So that's really, really difficult to do. But sometimes people are crazy and say, okay, it's really difficult to do, but we'll do way more. Let's try 1 kilometer resolution simulation, because why not? Sounds impossible, but of course, if I talk about that, it's not. So first you can say, okay, I have a better resolution, I can have a better accuracy. It's normal, but I have way more data to process, of course. But that's not only that, because you can say also, what's really important is to say, I can simplify the computing, because if I have really big cells, I have to make a lot of assumption in them. So I have to have really complex kernels to be sure that, of course, I have a 200 kilometers cell, so I don't really know what's going on. So I have to have a model to pretend that, oh, I know roughly what's going on. And that's really difficult to do. If you have smaller cells, you don't have to do that. You can use classic equation and say, okay, that's 100 kilometer resolution cell. I can draw up a lot of my big complex kernel. So you have less bugs, you have less assumptions, you have simpler models. So simpler to develop, simpler to debug, simpler to test. Really nice. And they want also, because it's not difficult enough, they want to incorporate the cycle of water, the cycle of energy, and the cycle of carbon, because of course having only atmosphere, ocean, and land is not enough if you want to simulate the climate for long-term simulation to know what's going on. And of course they did it. So that's presentation from Danny Clock from the Max Planck Institute of Meteorology. So that's really, really huge achievement that they did with this team, of course. So it's a big teamwork, and they run on Jupiter, of course. So 24,000 GB 200. So this kind of this kind of hardware here. So 1 exaflop, top 4 of top 500, and ALPS. I already talked about that of ALPS simulation last year. So 11,000 Grasshopper. So 0.4 exaflop, still really big. So 8 in the top 500. And what they did is, okay, we have a 1 million line of code simulation based on Fortran and OpenSCC. And of course, they want to optimize everything. And they said, okay, first thing, we have a problem because we have 10 to the 12 degree of freedom. That's a huge problem, in fact. And practically half of the code base is composed of pragmas, just to tell, okay, OpenSCC does vectorize, do this kind of stuff, as Vashon mentioned also in his Fortran presentation. And for them, it's a problem because they want to have portability, so they avoid this kind of part and to stay on the classic Fortran and do some weird magics with NV Fortran, for example, as Vincent mentioned also and Vashon showed us in his presentation. So that's really powerful, and you can have more flexibility because, of course, the compiler does the work for you. You don't have to explicitly call OpenSCC for that. And there is a trick, because Ocean is slow once you are doing the simulation, so they run this part of the simulation on the CPU, so on Grace here. And the atmosphere is fast, and you run the atmosphere simulation on the GPU, so on the Hopper for the simulation. And here you can balance your simulation naturally, because you can do more complex stuff, but more slow stuff on the ocean, and more fast and simple stuff on the atmosphere. So that's one of the tricks they had. Of course, they have a lot of small kernels, I explained before, so they use a lot of CUDA graphs to be sure that they can schedule everything, and the cost of starting the kernel is not too much, because otherwise you wait a lot. So they did all this kind of optimization, and of course they managed to simulate 145 days in 1 day of simulation on Jupiter, which is huge. It's the same performance roughly that Econ has with the state-of-the-art, with only the ocean, the atmosphere, and the land, and they had the carbon, they had the water, and they had the energy cycle on top of all the other, of course. So of course it's not enough. They want to add more cycles, they want to have more interaction, but it's ongoing. And the next step for them, because of course, once you archive something, it's possible you want to do more, is to try to have 150-meter resolution, because the point is right now nobody knows what clouds are doing in a warmer climate because it's too small. You don't have the information. With 150-meter resolution, you can have this information and you can do some simulation with that. So that's the next part they are doing. I'm not sure if they will be ready for the next year GTC, but if they are ready, of course I will talk about them, because it's really good to be able to do this kind of stuff. So yeah, it's roughly 1 hour. So let's talk about a little bonus for this session, and then we will stop here. So let's talk about 3D model scanning to introduce the topic. So if you have a model, a real model, and you want to make a 3D asset of this model, the classic way is to say, okay, I will take a bunch of photos of this model from many angles, and at some point I will manage to have a point cloud of all my model, and by a lot of tricks I can get to my 3D model and everything is nice. Of course, it's a big problem. It's horrible to do. It's really computing heavy, and of course a lot of tricks were done. So you can start with rasterization, and it's okay. It's a bit slow, but it's okay. At some point, you will try to scan some glasses, and of course, it's not working on glass because you have reflection and your point cloud is a bit messy and you have a lot of problems. So, okay, we are stuck. We can do more. We can wait until 2023, until the nerves are coming, so the neural radiance fields, and they do manage the glass. So if you want to scan a bottle, a glass, whatever you want, it's okay, no problem. But of course, if you have a lot of detail in your model, for example, you want to scan a tree, you don't have transparency, but all the leaves are a lot of details. And the problem, of course, is your nerve is stuck and the rasterization is broken also. So you will have a blobby shape and not a tree, and really weird result. Okay, that's a problem. The other problem of the nerves is it's slow. So you need 10 seconds to render one frame. So it's really slow. Okay. And we have a new player in the game now. It's Gaussian Splat. And Gaussian Splat, they can also manage glass. They can manage detailed models. So if you want to scan a tree, it's okay. And they are practically real time. We have to work a bit, but it's practically the case. It's way more faster than the nerves. So let's try to do that. So the point is to make sure that you can train model to drive vehicles. And that's a big problem because, of course, if you want to do that, you have an environment. You want to render your environment as a 3D scene. If you do it in Blender, for example, you have your street, you have your road, you have your trees, your lighting, everything, and you render that, and you feed that to, you have images, and you feed these images to your model, and you say, okay, drives, and we'll figure out where you are going, and we will render the scene and give you another image, and you can do that. Of course, that's a problem because you want to do that many times. You want to do that for a lot of situations. And if, for example, you say, okay, I have a road, I want to train my model to go around the crate if there is a crate on the road, for example, to be sure, to be safe, you have to change your environment, to put the crate in your environment, to re-render your environment, and to get a bunch of images to your model, to train the model to go around the crate on the road. And that's horrible, that's really slow, and it's not really efficient, and of course there is a problem. And at some point, Omniverse New Rake come into the game, and they are based on Gaussian Splat, of course, and this model is trained by real-world images, and the goal of this model is to generate other realistic frames as fast as possible. And the good point with it is it's based on Gaussian splat, which is really flexible, and you can generate a lot of variation of this image. So here you can say, okay, there is a car, maybe there is it the other way, or maybe there was someone else here, there was someone walking on the street. On the fly, you can do that. And this team start to think, okay, what if Nurek is real time? If it's real time, maybe we can do some stuff. The goal is to say, okay, let's remove all this part and just use Nurek, generate some images on the fly with a model driving car, and make a loop on this with low latency and see what's going on. And of course, it was not exactly what they did right now, but they came to something really nice, which is Alpha Dreams. And the idea of Alpha Dreams is to say, okay, we can have weather on demand, so you can have a street, some blocks on a city, and say, okay, it's sunny, it's rainy, it's cloudy, snowy, it's a day, it's night, or whatever. You can on the fly say with a prompt, what is the scene? So it generates 12 frames at a time. So each time you ask Alpha Dream to render, you get 12 frames in the future. So the most probable frames. So remember last year I presented Blackwell RTX, and Blackwell RTX is capable to generate 4 frames in the future. So hardware itself is capable to generate 4 frames in the future at a time. Here it's 12 now. They upgrade also that with some tricks. There is a multi-camera generation. So there is up to 4 in their presentation. Maybe it's possible to have more, but the idea is if you want to simulate a driving car, the car has a lot of sensor, a lot of cameras, and you can say, okay, I have a front camera, but I have 2 cameras on the side, 1 camera on top, maybe something like that. So you can simulate all these point of view at the same time with Alpha Dreams. And it's 16 frames generated at a time for the multi-camera, but it's not really important for this slide. And they are keep 54 frames per second on the B300, which is huge. In fact, you have to do it. It's really difficult to achieve that. And of course, what they did was to train the model on 100,000 of hours of recording. So with the neural Gaussian splat, so you have the flexibility of the Gaussian splat, and you can edit everything you want with a prompt. So with a prompt, you can say, okay, it's rainy, it's sunny, whatever. Or there is a crate on the road, and there is a truck passing by, or there is whatever. You can do whatever you want. And they plug a wheel, a driving system on it. And of course, JSN play with it because, of course, it's really nice to have this kind of stuff. And the point is, you talk to the model, you tell the model, okay, I'm here in your environment, I'm driving through this one, and the model on the fly generate what you are supposed to see. So here you can say, okay, it's a bit foggy, it's night, I'm going in this direction, and that's really powerful. Of course, you have some limitations, because if you are saying, okay, it's really rainy, at some point you will have some glitches because you are going a bit away of what the model learned and what the information it has, but still it's real time, it's really nice. And there is no collision yet in the model because, of course, it's just a proof of concept for now. But the point is, of course, they did a demonstration on stage. The only demonstration of stage I saw on this GTC. And they start with the engineer. So this is a team responsible for this work. And at the end, of course, they invite people from the audience to play with the driving car. So here you have the position of the driving wheel, and you can have a prompt. I don't remember where the prompt. It should be here somewhere. So you can tell which weather you want to have, and then you drive, and the model will generate on the fly the image you are supposed to see. And of course, at the time people realize that there is no collision, they do crazy stuff with it. They turn into bushes, turn into a house, something like that. And of course, if you are driving a bit too far away, the model at some point will tell you, okay, I don't know this part of the city, so go back, because I don't have the information. But still, having something real time, you can drive in a generated environment with Gaussian-Splat. There is no triangle, there is no vertices, there is no rendering. Everything is real time on a big GPU. Here you can see the computer here with the B300 in it, but still it's really powerful stuff. And thanks for your attention. And here I have a link for all the notes I took from this GTC. So it's huge. Of course, I cannot put everything in the presentation because it would be too much. And I can show you the summary here. So all the notes I took from this GTC. So you have the link in the presentation if you want to have a look. So here are the keynotes. You get the hardware news, the different hardware news. So new liquid cooling stuff, new compute paradigm. Of course, I don't have time to speak about everything, but everything is interesting, of course. The news, CUDA new feature and beyond, Qtal programming from Bryce, Stephen Jones from the new feature and beyond. We have Jan also was really interesting, really technical, but really interesting. So in fact, you already had some glimpse on their presentation, on the presentation I did for the GPU architecture, but you have all this information. So all the notes I took, the simulation part, the IA stuff, the quantum computing, the gaming. Didn't manage also to fill these notes. I have to do that, of course. I forget, but we have also this kind of news. So if you are curious, you can have a look. And if you have some question, or maybe it was dense, I don't know, on that, can answer them. Okay, so question from Vincent. It was a pleasure. Thank you very much for this very digestible presentation. Yeah, it's try to be reasonable because last year it was a bit dense. The year before it was 2 hours and a half. So I try to be as clear as possible. Of course, you have. I'm pretty sure if you want to have some news with more hardware, as I mentioned, you have news about direct liquid cooling. You have news about people who are doing crazy stuff, giving 100% of cooling on full rack, so they cool everything. They cool CPU, GPU, the switch, the memory. So you have crazy stuff, but I don't have time to talk about everything, of course. Before, thanks for the presentation. Okay, so you don't have some question, but you are happy. So that's the principal point. Okay, question from Vincent. I have a question since I haven't yet done the previous webinar. Can I follow along with some resources? All the webinar, you mean? The GTC feedback or the webinar of for example, the Rust of last week? Or because if you want to follow, normally you have everything on YouTube. The last week Rust, etc. Okay, you can have a look on the YouTube channel. So you have the YouTube of ROCC FR here with Mary and Karim. You can also have a look to the. Okay, Mary, you put the link in the chat. It's really nice. You can have a look to all the webinars. So we have not remember 17 right now, 16. I don't remember. A lot. And you can have a look to all these webinars, of course, with as we do today. So you have the webinar, you have the question, you have everything. So you can see if you want. Question from Isabelle. Thanks for this presentation. Really clear. Yeah, not dedicated for GTC 2026. Apparently, I forget some part of my notes, so I will update everything quickly. I will try, but of course I have a lot of stuff. If you want some information, if you want some data sheets, if you want the presentation, stuff like this, you can ask me. If you will need to have extra information, that's okay. But yeah, this year I followed something like 40 presentation, I guess. I don't really count now. Last year it was a bit too much. Last year it was 70. The year before it was 90. It was really too much. This year was a bit reasonable. It was only 40 or something like that. But yeah, if you want more information, don't hesitate. You can ask me. No problem. In fact, I do this work for you, so no, that's the point. So no problem. And maybe I did not mention that, but of course for Dynamo, I'm pretty sure at some point we'll be able to trick it to do some classical HPC workflow in it, to have a split of data, to have this kind of stuff, to manage that in a really nice way and smooth way. Here it's oriented for machine learning, but of course you can trick it. You can use a PyTorch to make some computing as we show in the school. So it will come. Of course, everything is related. You don't have the machine learning and the HPC. They are working together. So will be interesting at some point also. Okay, we have still a bit of time, so if you have some question, even if, of course, there is many thanks in the chat, so normally if there are many exchanges, that is the time to stop. But if you have a last question, it's okay. Question from Guillaume. What about the portability of a code relying on Qtile? You will have a nice portability on every NVIDIA devices, of course. And I don't know if... Thank you, Guillaume. I don't know if the Rust implementation. I do have the Rust implementation. I did not have time yet to play with it, of course, because I do too much thing at the same time. But I'm pretty sure I will try to play with it. Maybe not before the school, because it will be difficult, but of course before the school of the next year, to make sure that I really give you some feedbacks on it. But maybe with Rust, with the design, if they did something smart with a CUDA oxide in a backend, it will be possible to have a backend dedicated to AMD GPU or Intel GPU, and maybe it will be possible. I don't know the people related to this project, so I don't know if they are really linked to NVIDIA engineer or not, or if it's totally free and they can do whatever they want. So we will see with time. But that's a really good design, in fact. If you are motivated, maybe you can try to implement a generic tiling system for everyone. Should be really nice. That's really powerful. And of course, we'll talk about that at the school. I'm not sure if we will have that time for this school, but of course, for the next school, we'll have time. So we'll do that, of course. For Python, for sure. Maybe for C++ next year. But for now, it's a bit too just for me to play with Qtile. I don't have the CUDA 13.3 yet, so don't want to break my computer before the school, of course. So maybe we'll wait for next year for the Rust and for the C++. But we can have some glimpse for the Python for this school. What about next week? Can you talk about what will happen? Oh yeah, last transition, Mary. Of course, I have to forget. So next week is a bit special. So it's not a webinar as we do generally. It's to really dedicated to answer all your questions related to the school. So how can we get the lectures? How can we get the containers? How can we use Pixie? Because Pixie is really powerful for a laptop, for a server, for a learning platform, all this kind of stuff. So we'll answer everything next week. So if you have some questions, if you want to check for your particular laptop, your particular computing center, it's a place to be if you want to be sure that you will not struggle during the school to fight with configuration. The point is to make sure that you can do that really before the school. We'll have then an extra week to play with it, to be really well prepared for the school. So normally should be nice. Okay, so we are right on time. So if you still have questions, it's okay. But if it's okay for you, maybe we can and wait a bit and then we can close at some point. Okay, sounds like an end. So thank you everyone for attending this webinar today. So thank you, Mary and Karim for the presentation, for the support, and for the school. Thank you everyone also to attend the school and to register, because of course it helps us a lot to see that what we are doing is relevant. So thanks again, because of course if there is a school, it's because of you, because you attend to the school and you follow the school and you follow the webinar. So many thanks to you. And see you next week. So we'll do some magics with the lecture, with code server, with Jupyter, with a learning platform, with jobs, scheduler, stuff like this. So if you have some question, don't hesitate to attend next week. And that being said, have a nice day and see you next week. Bye.